Good afternoon, everyone. Welcome to the first module for our 2026 Center for Fundamental Physics of the Universe AI Winter School. Just a reminder before we begin that you may ask questions in the Q&A. Please don't try to speak because we won't be able to hear you. But if you can write your questions in the Q&A, we will try to address them during the presentation. And without further ado, I should introduce Sean Dubé from Brown, who will be leading the introductory module. So take it away, Sean.
Okay, thank you. So this introductory module, by the way, thanks everybody for coming. This introductory module is meant to be a very basic primer on AI, an introduction to AI. So basic concepts, basic tools, and also an introduction to how to get used to using some libraries like, I don't know, Pandas or Google Colab, things like that. It's not meant to be exhaustive. It's meant to get your feet wet and to give you the tools you need to start doing things on your own. The way this is structured, there's going to be a short lecture and then a hands-on, which I will walk you through. In the hands-on portion, we'll look at some data, and then we'll build and train a neural network, and then you get to ask some questions. So without further ado, let me get to the lecture portion. And as Jan said, there is a time to ask questions. The lecture part is broken up into two pieces. The first part is the intro to AI concepts. The second part is the intro to the hands-on. And so in between that will be the time for questions. Yeah, so as I said, this is a machine learning primer. So if you know nothing about AI whatsoever, you're in the right place. If you do know a little bit, then this may be a refresher for you, which is good. You should always do refreshers. So what is machine learning? So when I first did this winter school module a couple years ago, I asked ChatGPT in an earlier version, I think 3.5, about what it thinks AI is. So AI, it defines as the development of computer systems capable of performing tasks that would typically require human intelligence or human level reasoning. ML is a subset of AI that focuses on development of algorithms, statistical models, learns from data, learns to make predictions. So all ML, all of machine learning is AI, but not all of AI is machine learning. So there's a distinction that you need there. Keep that in mind. And this definition is from a book, a very good book by Raylene Garon, if you want to get into machine learning using particular libraries, Keras and TensorFlow, which we'll get into later. I highly recommend this book. So what is machine learning? And so if you notice here, this definition, where is that? That's 1959. So people have been thinking about this for, I don't know, almost 70 years. So even though there's been an explosion in the interest of AI in the last, I don't know, 5-10 years or so because of the advent of large language models, the concept of machine learning is not new, not at all. So an early definition given by this person, Arthur Samuel, machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. I think that's a great definition. And if you want a more engineering-oriented one, this guy, Thomas Mitchell, down here, 1997. But the point of it is, machine learning specifically is programming computers to learn from data to make predictions. And again, this goes back quite a long way. But in recent years, of course, there have been the advent of new algorithms such as self-attention, the advent of very high-performing GPUs, data centers, et cetera, that have made things possible that were not possible in 1959 or even in 1997. So some types of machine learning architectures. So artificial neural networks, decision trees, there are unsupervised learning methods such as clustering methods, and many more. There are lots of things that fall under the label of machine learning. And today we're going to look at what artificial neural networks are. So yeah, artificial neural networks. So what are artificial neural networks? Excuse me. So Artificial neural networks are called artificial because they are contrasted with biological neural networks. Right? Biological neural networks, like the one you have in your head, consist of this cell and all its attendant structures. An artificial neural network, it tries to model the biological neural network, not really, at least not this particular architecture, but it also has some sort of cell with some and its attendant features. So an artificial neural network has an input like just like the one in your head has some cells. You have the inputs get some weights associated with that. We'll talk about that later. Has a bias, an activation function, and an output. So just like the biological neural network in your head, the artificial neural network will take some inputs and spit out an output. It'll think about things. So this is an artificial neural network. Just one sec. Let me check something real quick. Okay. So this is an artificial neural network. It doesn't look like much without any explanation, but you can kind of see how it tries to mimic your brain, your own biological neural network. So you've got an input. I just kind of arbitrarily labeled this side as an input. You've got some things called hidden layers, which are the layers between the input and the output layers. And you have some number of these things. So the number of each of these hidden layers and the number of these nodes constitute the structure of your neural network. And each of these is called the hyperparameter. We'll contrast that with parameters such as weights and biases, which are the learnable parameters. Hyperparameters are tunable but not learnable. So this is a key equation in artificial neural networks. What are they? So H is your neuron output, X is your input features. So for example, if you're trying to model, particles, input features may be mass, momentum, charge, spin, et cetera, et cetera. Weights and biases are the things that are learned. And phi is the activation function. So if you have your input features, you can weight them by these learnable parameters. And then the output of the network and then the activation function will give you the output of the network. So what you need is to give the neural network your input features, and then it's through an iterative process is going to learn what the weights and biases are. Once you have those, the activation function is going to give you an output, and that's going to give you some answer. So remember, the key thing here to realize that weights and biases are trainable. These are parameters, not hyperparameters. Hyperparameters being the number, again, being, for example, the number of hidden layers, the number of these nodes, etc. These are the hyperparameters. Weights and biases are the parameters, i.e. learnable parameters. So the activation performs a transformation. So this phi function performs a transformation on these things. It adds nonlinearity to the model. Nonlinearity is good. It helps you learn complex mappings between the inputs and the outputs. And there are different activations for different tasks. So one example of an activation function is the rectifier linear unit, also known as ReLU. It is used for, among other things, mitigating the vanishing gradient issue. Vanishing gradient, you'll understand in a few minutes, but it's basically a problem with neural networks, especially deep neural networks, where the gradients go to zero, the neural network stops learning. Another activation function is called the sigmoid activation function. It's a common choice for binary classification, i.e. classifying between cats and dogs, or apples and bananas, or pizza and calzones, something like that. It saturates between 0 and 1, so it has these two different binary states that you can get. For multi-class classification, the softmax function, which is not shown here, is another common choice. But the point is there are many activation functions that have many different uses. And your job as the model builder, engineer, data scientist, physicist, whatever, is to choose the right one for your task. So a quick aside on binary classification. For binary classification, a common plot or figure of merit metric to produce is called the receiver operating characteristic curve, or ROC, and the area under the curve, AUC. The ROC plots the true positive rate versus the false positive rate, and the area under the ROC curve is the AUC. So an AUC of 50%, and we'll during the hands-on, this will be made concrete to you. An AUC of 50% says that your classifier, your binary classifier, does no better than the flip of a fair coin. It's just chance. So your neural network, your classifier, whatever you decided to create, didn't learn anything. The goal then, or one of the goals, is to get your AUC close to 1 as possible without overfitting. And I'll get into overfitting in a little bit. So if you perform a binary classification task, i.e. cats and dogs or apples and bananas, then to see how well your neural network did at learning the difference between cats and dogs, this is one of the metrics you may use. And I'm bringing this up now because it'll be in the hands-on. And here's an example here. So this whole thing here is the ROC curve. So you have the true positive rate on the y-axis, false positive rate on the x-axis. The dashed line is the 50-50 line, the 45-degree line. So the ROC curves, the blue and the orange, are sitting at more than 0.87, so 0.875 each. What this says is that on the test set, when you train the neural network and you evaluate the performance, excuse me, on data that it has not seen before, it performs very well. Excuse me. So almost 88% of the time, it can classify two different things correctly. What does the train curve mean? It means that during training, the data that it does see, it is able to perform also well. However, if the train AUC is higher than the test, that means then your model is starting to overfit, meaning it is starting to memorize features of the data that it cannot use to generalize. In other words, it starts to stereotype the data and it does not generalize very well. So stereotyping is bad. Hopefully we all learn this. So for binary classification, which we're going to do in the hands-on, this is a key plot that you have to keep your eye on. So back to artificial neural networks. One important theorem is the universal approximation theorem, and it approximately says artificial neural networks can approximate functions provided there is at least one hidden layer. Again, this is approximate. There are more rigorous definitions here. But if there is a mapping to be had in a supervised learning task, like we're going to do with hands-on today, then the neural network should be able to approximate whatever function maps between cats and dogs, the features of the cats and dogs and their labels. So whatever underlying function there is, the universal approximation theorem says your artificial neural networks can find this approximation. And that can be made more mathematically rigorous, and as such, it gives us confidence that neural networks can, at least in principle, do what we tell it to do. So now that we have the basics of artificial neural networks, how do they actually learn and what do they actually do? So the idea is to try to minimize a loss or cost function. So I have an example here. This is called the mean absolute error. It's a common loss function that's seen in machine learning. Other ones are the mean squared error, the root mean squared error, other things like that. But the idea is to minimize this guy here. And what are the things? Y is some true value. X is some predicted value that your neural network tries to spit out, and N is the number of data points. So during the learning process, or it's a supervised learning process, if you have some true values that you're trying to predict, and your neural network is learning and trying to get close to these true values, this loss function will tell you how close you get. You need to tell the model how to optimize this loss. In other words, minimize the loss function. So you get closer and closer to the correct value. So there are different losses for different tasks. Mean absolute error for regression. So regression is not classification. Regression means you're predicting continuous value. So instead of predicting cat versus dog, you're trying to predict the length of the dog's tail or something like that. For binary classification, predicting discrete values, cat or dog, for example, there's a loss function called the cross entropy, or for binary classification, it's a binary cross entropy. But the mean absolute error is just simple to write down. It gets the point across quickly. So different losses for different tasks. Your task is regression. There are a whole bunch of losses like the mean absolute error, the mean squared error, etc. binary classification, cat versus dog, there is a cross entropy or the binary cross entropy. And again, it's the model builder's job to decide what works the best for your task and what your task actually is. Is it classification, is it regression, etc. So learning, how does a neural network actually learn? I mean, we have the loss function. We know what we're supposed to do with it. What is it actually? How do you actually do this? Well, we use an optimization algorithm called gradient descent to gradually modify the model parameters until the loss function, whatever you choose here, is at a minimum. So gradient descent measures the gradient with respect to a parameter vector, theta, and moves in the direction of steepest gradient. So it's like the common analogy is if you're standing on a hill and you want to get down into the valley or something, and it's kind of foggy and you can't see your way down, you kind of feel with your foot or your hands or whatever the path down and you try to see which is the steepest way. So in reality, this is not very safe, but in the analogy here, you want to get down the fastest way possible. So you feel around for the path of quickest descent. That's kind of what we're doing here. When the gradient is 0, you're at a minimum, hopefully a global minimum, not a local minimum. If you're at a local minimum, you're not necessarily at the optimum value. And so there are ways to kick yourself out of local minimums, but we won't go through that today. And so the goal is to reach the global minimum and not get stuck in a local one. So loss functions, ideally, should be smooth and convex functions. But that's the basic idea of how these neural networks learn. You pick a loss function, you optimize or you minimize it with this gradient descent algorithm. And there are different optimizers that build out this stochastic gradient descent, computes the gradient based on random instances of the training set. There are improvements on this called ADAM or NADAM and many more. But they all work to minimize your loss function here. And can we be slightly more concrete about this, slightly more rigorous? Indeed, we can. So remember, theta is your parameter vector. Eta is a hyperparameter. It's the learning rate. So how fast your model is updated. This symbol here, everybody should be familiar with. Gives you the gradient, and then F is your loss function. Okay, so the updated weights are given by the current weights minus the gradient of the loss function with respect to some parameters. Okay, so if you look on the plot on the left, so the cost of the loss function here is on the y, and then the parameter values, whatever parameter vector you have, is here. And so this parabolic curve here, which I've taken from this very excellent book down here, this is called your loss curve. And the idea is to optimize your loss function here so that you get to the minimum of the loss curve here. And each learning step, how big these learning steps are, is given by the learning rate. So your model parameters are updated based on this algorithm, gradient descent, which just takes the gradient of the loss function with respect to the model parameters until you get down here. Now, so your model parameters are, again, I should say, are the weights and biases. So I didn't make that concrete before. So let's take a quick look at this learning rate here, because it can be very important. So if you try to optimize your parameters with this gradient descent method, but your learning rate is too high, you'll never settle down to a stable equilibrium down here. You're just going to jump around the loss curve, and you'll never settle. And then your learning rate, and then your model will never learn. If your learning rate is too low, then it's going to start you'll never get to the minimum, at least not in any reasonable time. So the learning rate, a hyperparameter, is something that can be optimized, just like the hidden layers or the neurons, i.e. nodes in the neural network. This is something else that you can optimize. And the way there are many ways to optimize them. There are libraries that can help you sort of automate or semi-automate this optimization for you, the hyperparameters, specifically learning rate. But the key takeaway here is that you have a loss function. You take the gradient with respect to your model parameters, and then you update them such that you keep going down toward the minimum of the loss function. So you have the loss function, you apply this gradient descent algorithm to optimize your weights and biases such that the loss or the cost is at a minimum. That is the very, very basic idea of how these artificial neural networks are trained. So to just tie this off a little bit, tie the learning part off, the information flows from the input to the output and creates what's called a feed-forward neural network. So you have your neural network, you have your loss function, you've set up your algorithm to do gradient descent, and don't worry, you don't have to hand code any of this. This is all done for you. But if you do, it's a great way to actually teach yourself how to do this. What's under the hood. But anyways, so information flowing from the input to the output creates a feed-forward neural network. Backpropagation efficiently computes the gradient. So you have feed forward neural network and backpropagation. These are very key components in machine learning optimization. Approximately what this means is the feed forward pass makes a prediction, it determines the error, and the error gradient is propagated backward into the neural network, and the error contribution from each layer is determined. Then gradient descent is used to modify the weights based on that. So it goes forward, backward, and this gradient descent algorithm will take you to your minimum loss. Hopefully by that time, your model weights and biases will be at the optimum value and your model works as you intended for whatever purpose you have. So another key aspect to take away is that the learning process is an iterative one, and you need to iterate this many, many times. Thankfully, modern neural network frameworks have a way for you to just do this. You don't have to hand code everything, but I encourage you to hand code things when you first start, just to help you learn things. So there are problems with learning. All right, so vanishing and exploding gradients. I mentioned this a little bit earlier. Vanishing gradients are when the gradients, so the gradients here, become too small during back propagation. The model doesn't learn. So it can be too small, it can go to zero, but there are ways to overcome this. So it can be mitigated. Vanishing gradients can be mitigated by choosing a better activation function, for example. That's why there are many different activation functions that were developed. So for example, the Rayleigh activation for convolutional neural networks. Exploding gradient is the opposite problem. The gradients become very, very large, exceedingly large, causing the instability in the model, instability in learning. And this can be mitigated by, for example, tweaking learning rate. Remember, I said that the learning rate was a hyperparameter that you can tune. So you can do that. Again, change the activation function, or in the context of deep convolutional neural networks, which we won't get into today, but they are very important in the world of computer vision. You can add something called a skip connection. And that's what a residual neural network is used for. You just type in residual neural network into your favorite search engine. You should read the seminal paper. Came out in 2015. Very, very interesting. Very, very key to modern computer vision. But it's outside the scope today. The point is that you can't just set a model, hit enter, and have it go and expect it to learn. There will invariably be problems. And two of these problems are the vanishing and exploding gradients, which there are known and tried and true methods to deal with. There are also problems with fitting. So what you're doing here is it's kind of a fitting problem. Of course, as you may know, you have problems of overfitting and underfitting. Hopefully a lot of you are familiar with this already, but in the context of machine learning, overfitting, as I mentioned before, is when the model memorizes features of the training set and it cannot generalize to data that it hasn't seen before. So when you unblind the test data, the model performs poorly. It can't do what you tell it to do. It can't tell the difference between cats and dogs on a blinded data set, even though you've trained it on cats and dogs. So in other words, the model stereotypes the training set, and as such, it cannot really generalize to unseen data. And there are, of course, ways to deal with this, as you may have guessed. One of the tried and true methods is just to add more training data. If you have more training data, it gets a more diverse sample to look at. Also, you can make your model simpler. There are things like regularization, which simplifies the model. You can use early stopping. What this means is that during your training, if you set it to train for a little while, you can tell the model, hey, monitor some metric like the loss function during training, and if it gets small and it starts to grow again, well, stop it before the point that it starts to grow again, because once the loss starts to get higher, it means the model is starting to overfit. You really want the loss to stop. So you can tell the model to monitor the loss and tell it to stop before it starts learning too much or too well, starts to stereotype. And again, these are things that these are built into model frameworks. And the other thing is to add a dropout layer. A dropout layer is something where you can put in your model and it drops out. It turns off nodes in your model and sets them it sets them to zero essentially. And what this does is it's another way to simplify our model. So all of these are ways to mitigate overfitting. It's a way to mitigate your model stereotype. You don't want it to stereotype. So there are tried and true methods to deal with this. And so again, you shouldn't expect your model to work out of the box. It's great if it does. If it doesn't, and you do some debugging, you find out it's overfitting, go to one of these. And again, the way you figure out it's overfitting, especially at least in a binary classifier, is to look at the ROC curves. If the AUCs are wildly different, like the train is much higher than the test, then you've got some overfitting. You've got to figure out how to mitigate it. Underfitting is the opposite. The model doesn't want to learn for whatever reason. It doesn't even memorize the test set. So there are a couple. This is slightly more complicated, but not that much more to debug. What you want to do first is you want to check to see if the model can overfit on one or two or a few training instances. So if you find your model is not learning, you actually want to create a problem for it. It says, okay, well, you're not learning. What if I just give you one image? So if I give you just one picture of a dog, can you just memorize what this dog looks like? And if the answer is yes, then okay, you know it can do something. So you have to figure out, well, what else do I need here? Is my data unbalanced? I.e., do I have equal number of cats and dogs? Do I need to pre-process the data somewhere? Do I need to re-engineer? Do I need to engineer other features in the data to make it learn? Or do I need to alter the model architecture or simply add more data? So once you debug, once you can verify that the model can memorize at least one training instance, if in the case of cats and dogs, it can memorize what one dog looks like, then you can go on and check what else you need to do, whether it's feature engineering, altering the architecture, adding data, or whatever. The key point is, from all of these, there are problems with learning, but there are tried and true and well-trodden paths to fix this. And so this is my quick tour around the world to artificial neural networks. I will end here before the hands-on, and I will take questions if you have any right
And again, if you have them, please type them into the Q&A, because that is how we can actually get your questions. So we'll wait a minute, and if you have questions, please type them in.
Yep. Wait a few minutes, and I will set up the hands-on.
So the first question is about physics-informed learning. To inject knowledge from physical laws, does the machine learning, especially data-driven learning, require a precise definition of data structures when data is viewed not as a structured set of samples?
Yes, I would say so. The data structure is so we're talking about physics-informed neural networks, but the question is more about, if I understand it correctly, what the data actually looks like. So
yeah, I will also point out that tomorrow morning's first session is devoted to physics-informed neural networks. So
you still do need to decide how to structure the data, but in physics-informed neural networks, tomorrow would probably be a better way to do this, to learn about this. But the quick and dirty answer is, you do need a precise definition of your data structure, and different problems require different structures of your data. For example, in particle physics, if you're doing jet tagging, there are ways to structure the data, such as a cloud, that work better when you're performing the jet tagging data set. rather than having them as simply a list of different particles within the jet. So the answer to your question is yes. A precise definition of data structure does help. Hope I answered that. If not, please do feel free to follow up here or online.
The second question is, how come the method works with continuous values, given that you're summing sample values for individual samples? There wouldn't be an integral and a discontinuous set of values.
Right. Okay. So I should share my screen, or maybe I can just explain it. So the you're not integrating over the values themselves. You're summing over each of the instances. Maybe I should share my screen again. One sec. Share screen. Right. So where was that? So yeah. So we're not integrating over the values of of whatever the values of the parameters are continuous, but it's I runs to the number of data points. So that's why it's a sum. It's a discrete sum because you have a discrete number of data points here. So it's not that we have it's not that the input values, for example, the length of a dog's tail is obviously a continuous value. But here the sum is just over the data points that you're giving it. That's why it's a sum, not an integral.
The next question is recommendations for good textbooks that dive deeper into neural networks or other ML architectures. You mentioned one at the front.
So that's the one that I used. I highly recommend it. It's more focused on, let's see where I can find, where is it? Yeah, here, hands-on machine learning with scikit-learn, Keras, and TensorFlow by Aurélien Guérin. It's more about Keras and TensorFlow, but I recommend this one to get in your feet. This is the one I used, and I work mostly with TensorFlow. There are other frameworks like PyTorch and JAX, JAX, which is Google's thing. So there are books about those, I'm sure, but I don't know the names of them off the top of my head. There are standard ones that I'm sure you could look up online, but I do highly recommend this one for starting out.
So since you have the slides up, can you bring up the slide that highlights the difference between parameters and hyperparameters again?
Sure. So was there a specific question?
Just to repeat the difference between the two.
Yeah, so if we take this as a model of a neural network, and this is not the only model of a neural network, this is an example of a fully connected neural network. So let's call these blue circles neurons. So all the neurons are connected to all the others in the layers before and after them. So the number of neurons and the number of layers, i.e. the hidden layers between the input and output, are hyperparameters. These are not learned during training. These are optimized. There are ways to optimize them, but they are not learned via gradient descent or anything else. Parameters, like the weights and the biases, are learned. You do use gradient descent to optimize these weights and biases. So trainable parameters are learnable. Hyperparameters are not learnable, but they are tunable. They tell you how to construct your architecture. Once you've constructed your architecture, then you can start to learn the weights and biases.
I think we're going to close on a much more speculative note. What do you think? How do you think quantum technology can change data-driven machine learning? I guess this is a question about quantum computing.
Right. That's an excellent question. And I'm not sure that I have an excellent answer for you because I am not an expert in that. So I think I will, if you want, you can email me. My email is at the top here. Email me. I know there is such a thing as quantum machine learning and there are algorithms for it, but I am not in any way familiar with them. So I don't want to give an answer here. But if you want to email me privately, and I can try and put you in touch with people who do know about them. but I don't want to give an answer outside of my area of knowledge here.
Fair enough. Okay, I think maybe we're ready to move on to the next phase.
Yeah, so the hands-on phase, I have a quick intro there. Let's see, where did it go? Yes. So we're going to do some applications of machine learning to simulated Lux Zeppelin data. And Lux Zeppelin, if you've heard of it, is a huge and the world's leading dark matter experiment. And so I'm sure most of you know dark matter makes up about 27-ish% of the universe, and it's called dark because we don't know what it is. We have an idea that it may be something called a WIMP, a weakly interacting massive particle. Weakly because it only interacts via the weak force, and we need to build giant detectors to detect them. And so Lux Zeppelin is the world's leading dark matter detector, in my humble opinion. And we're going to apply some machine learning concepts to simulated data and see what we can glean out of that. It's not the hands-on today is not so much about the physics of Lux Zeppelin, the physics of dark matter, or anything else. It's more about, well, here's some data that could be used in real-world experiments, and try and apply the concepts that you learned today to this data. And the idea is that machine learning is actually used in real-life experiments. Okay, so today we're going to be performing a classification task. In this case, a binary classification task, cat versus dog. But today we'll be talking about signal versus background, and you'll use the principles above to build your own model. I've set up everything, so everything is technically already done for you. However, you will have an opportunity to modify and or build your own model to see if you can do better than I did. And everything is kind of ambiguous right now, so let me make it slightly less ambiguous. So like I said, today will be a classification exercise. You will examine simulated LZ Lux Zeppelin S2 pulses. I will explain what that is in a second. And if you want to know more about Lux Zeppelin, you can click on this link below. And you will classify these pulses as coming from either multi-scatter or single scatter events. And let me explain what that means. So this is a schematic of Lux Zeppelin detector. It's a giant time projection chamber with liquid xenon as its active medium. So if a particle comes in and it strikes the active material, it'll give a prompt photon signal, which is called the S1 signal on the left, on the right here. It's a smaller signal, and there'll be some electrons that are drifted up in an electric field. And once it reaches this gaseous phase up here, it'll also release some light signal, and both these will be detected by the photomultiplier tubes at the top and bottom. The second signal that comes from this drifting is called the S2 signal, which is the larger of the two signals. So today you will be learning about how to classify particles based on their S2 signal. So if a particle comes in and strikes once, that's a single scatter. If a particle comes in and strikes more than once, and today we're going to work with only double scatters, it'll change the shape and other parameters of the S2 signal. So dark matter is only thought to scatter only once, other particles maybe twice. So this is a signal versus background classification task based on this S2 pulse here. And we're going to use simulated pulses, not actual data pulses, because they're simpler to work with and they're easy to generate. And so let me give you an example. So for single scatter and multi-scatter, i.e. SS, MS, or MS2 events, they're easily distinguishable by the human eye. Some are not. If there is a double scatter event, the time between the two scatters, which is labeled delta mu, where delta mu is usually in nanoseconds or microseconds, depending on what units you want to work on. Multi-scatter events with low time between the two scatters are very hard to distinguish between single scatter events, because these two scatters are more or less on top of each other, and it's hard to distinguish. It's hard to resolve them. Things with a higher separation in time, double scatters with a higher separation in time between scatters are much easier to see. And so if you look on the left plot here, this is an example of a double scatter or multi-scatter event here. You can see it's with a high delta mu, a high time between double scatters. And you can see by eye, it's very easy. It's very obviously much broader than the single scatter pulse on the right, which is much thinner. So by eye, these two are obviously different. You can tell which one is from the multi-scatter. You can tell which one is from the single scatter because of the time between the two scatters and the double scatter. But if the time between the two scatters and the double scatter delta mu is very, very narrow, well, then your pulse for the double scatter is going to look like your single scatter event. So you can't always tell by eye which is double scatter, which is single scatter. So you hope to train a neural network to do this for you. And also, computers can just process data faster. You don't want to look through a bunch of these by hand. Just something about the data structure, which gets to a question that was asked earlier about the precise data structure. Here, events come as time series data. So each of these pulses is given by a pulse train of 700 samples, which I've converted to nanoseconds here. But each pulse train is 700 samples long, and each sample gives the pulse height in PhD. PhD meaning photons detected per 10 nanoseconds. And in general, you can to help the neural network learn kind of a diversity of data. You can include noise in the data, and you can include a time jitter. You can jitter them along the x-axis, and you can add some noise. This will help them. This will add diversity in the training data to help the neural network learn. But this specific data set is time series data, and each pulse is a 700 sample long time series. Okay, and due to the nature of the data, the time series, you may think about what type of neural network architecture is better for you. So you have a particular data structure. And particular data structures may be more amenable to different types of architectures than others. So time series data, one common choice is a one-dimensional convolutional neural network. It doesn't have to be. You can use a fully connected neural network like I showed you earlier, but it depends on you. It depends on your data. It depends on what your data is structured as. But you may be wondering what a convolutional neural network is. So let me quickly go over that because it is in the hands-on. So convolutional neural network, a CNN, is a neural network model that is built from convolutional layers. And what is a convolutional layer? Convolutional layers are designed such that the neurons in the first layer are not all connected to the pixels, or in the case of three-dimensional voxels, in the input image, or in the case of 1D, these 1D pulse trains like the samples, but only to a subset within the receptive field. And the neurons in the second convolutional layer are only connected to a subset in the first layer, et cetera, et cetera. So let's make this a little bit confusing. Let's make this slightly more concrete. So if you have, so I took this image from the book that I mentioned earlier, which again is a very good book. So if you have an input image, you want to learn something about bunnies. You have this image of a cute little bunny here, and the neurons in the first convolutional layer, denoted by these little circles, looks only at a portion of the bunny, and another neuron looks only at the other portion. Second convolutional layer does the same thing. One neuron only has a receptive field of a certain subset of the neurons of the preceding layer. And so you can stack convolutional layers on top of each other, and then you can the features kind of filter up to the top. So that the neural network learns in a very structured way on how to reconstruct features of your input. It doesn't necessarily have to be an image. Like I said, it can be time series data. Again, it depends on what your data is, how your data is structured, et cetera. So neural networks have neurons that are assigned weights and that are learned during the training process. In CNNs, neuron weights are given by filters, which look for the features in the image. And the convolutional layer can have multiple features, and you can stack these. You can stack convolutional layers. And again, to be more concrete, if you have the cute little bunny here, and you have you can always have color channels, RGB color channels, or other things. The first convolutional layer can be a stack of different feature maps. And the second, so on and so forth. And these reconstruct the different features of your input image. So this is how a convolutional layer neural network works, by stacking feature maps in layers to reconstruct features. And it's not all of these nodes are not connected to the entire layer in the input. Whereas previously, if I can find that image, previously, where'd that very nice image go? Yeah. Here, all the nodes are connected to all the other nodes in the layers surrounding it. Convolutional layers do not do that. They work by reconstructing features in this way, looking at nodes within their own receptive field. So this is one choice that you have for the data for time series data. Generally, these types of neural networks are used for computer vision, but you can also use them for time series data. Yeah, so residual neural networks, as I mentioned before, are a type of CNN. They model some residual of the underlying function by adding these so-called skip connections, or yeah, skip connections. First developed in 2015 by Kecha et al. This is the archive paper. I highly, highly recommend you read this if you're at all into machine learning or computer vision, image recognition at all. This is a great starting point. And it was originally developed to deal with, among other things, vanishing gradients in deep neural networks. So that's a quick aside to get back to what we're doing here. We want to make a prediction. We want to classify this. We want to classify these time series data that we have here as single scatter or multi-scatter. And we have to decide, or you can decide, whether a convolutional neural network or a fully connected neural network or something else does a better job. There are many other options that you can use here, but besides these two architectures that I mentioned, but that's for you to decide. If we go to the hands-on, let me pause here for quick questions. Are there any questions about this at all?
Yeah, there are a few questions. One is your goal to make stochastic or deterministic classifications? Are you looking for a yes, no, or a probability of multiples versus single event in this?
Yeah. So so that's a great question. So you can at the end of the okay. So I can talk about this for a few minutes, but in the interest of time, I'll just say we're looking for a is it a single scatter or no? Yes or no? That's what we're looking for here.
Okay. So the second question has to do with looking at CNNs. The fact that you're using a CNN, does it presume that there's some local structure to the input? In other words, that there is some feature?
Yes. There is some feature that can be reconstructed. Yeah, within, for example, in the image or in the time series. Yeah. If it's complete noise, you're not going to learn anything, at least in this problem.
The next question is a little bit more complex, but it's ultimately related to the dimensionality of the problem. If the feature space for event waveforms, you said there were 700 unit time events. As you add more dimensions, how do you avoid the overfitting while keeping physically relevant separation between single and double scattering events?
Right. So just to be clear, if I have a pulse train here, there are 700 samples, time steps within this pulse train. That's what I mean. So within one pulse, there are 700 samples. And I'll show you this in the hands-on. If the dimensionality changes, like there are more samples in the pulse train, 1,000 samples, there are ways to mitigate the overfitting, or to if there are very hard pulses to distinguish. More data may cause weaker learning. Techniques that I mentioned earlier can often help, like regularization. There's also the idea of, especially with CNNs, there's the idea of data augmentation, where you add things to the neural network, such as a time jitter or noise to help it learn better. Different architectures, such as resonance, also will deal with these issues. I kind of lost the question there.
That was basically how do you avoid the overfitting due to multidimensionality.
Yeah, all those techniques that I mentioned before.
And then a more general question is there a general guideline to figure out which specific network model works better for individual problems? You mentioned this is a 1D train, so therefore a 1D uh, network would probably be better. Are there other rules of thumb?
Um, so for time series data, 1D CNNs, long short-term memories, RNNs, things that have been tried before are good to try again. Just experience in the literature. Usually that's what it is. And it also depends on the structure of your data. Like getting back to that first question, this actually does kind of matter in some cases. So different data structures, different models are more amenable to some different data structures, like particle clouds, more amenable to graph neural networks or transformer models to make better predictions. But I would look up what's been done before, or see what the strengths of what architecture has been used for what problems before, and then use those as your rules of thumb, and then iterate on that.
All right, that's it for current questions.
Cool. So all of you should have been added to a Google group. That Google group has been added to this year's share drive. It's the AI Winter School Brown Physics CFU 2026. You should find that under your shared drives in the Google group. You should have access to it. If you double click on this, you will find a list of different activities. The intro module here, you can double click on this, and then you can right click, and then you can say make a copy, right? And then in your own Google Drive, in your local Google Drive, not our shared drive, but your own drive, you should it should have copied it, and it should have created. If you look in the lower left, it should say created a. It should have renamed the file to copy of Brown CFP Winter School 2026 Module 1.ipynb. So if you go to that in your own, if you click on My Drive and open that, it should open that for you. You don't need to rename it at all. You can if you want. You don't need to. So if you open that and then go here, you should be able to edit this. You will not be able to edit one in the shared drive. Please don't try and don't ask. But you can edit one that's been downloaded to your own drive. So the first cell is just some intro info, but the first editable cell is your name. So you should, to keep track of things, you can put your name, your last name, just keep track of your own files, and the date. What's track of the date? 2026 0601. So this is Google Colab, I should mention. So this is just a Jupyter notebook in Google's framework. You can, to run a cell of code, you just hit enter, hit this play button here, and it'll work, and it'll give a little check mark when it's done. Or you can go into the cell, and on your computer you can hit Shift Enter, or if you're on a Mac, Shift Return. It'll also enter that here. By the way, I should say, if there are questions during this, please feel free to just put them in the question box. Okay, you don't have to wait till the end. And so the first cell is just to import some neural network libraries. Like I said, we're working with TensorFlow and Keras today. Keras is more the high-level API. But you can also import Torch, PyTorch. So the Torch library is does lots of tensor math to do more neural network stuff, like have convolutional layer stuff. You can do torch.nn. Torch. It's supposed to be as nn. Sorry for that. You can just hit run. Yep. So we won't be using Torch today, but it just to show you how to import these. So these are already installed in Google's environment. On your own system, you're going to have to install them yourself. Usually you can use a virtual environment or something like that to keep your system clean. but you don't have to worry about any of that today. Everything here is installed. Google has it covered for you. Okay. The next thing you're going to do is you have to mount your Google Drive. And for me, I've already mounted it before this. But for you, when you hit this, there's going to be a pop-up window, and you're just going to click give Google permission to access your drive, which is fine. And you have to do it a couple times. You just click continue, and there should be a next window or a next screen, and you have to scroll down and click continue again, just to give it. It's a little tedious like that. And if it gives you a checkbox and asks for permission, just say select all, and then scroll down and click continue. It's just so that you can read and write things from your drive. You're just mounting your drive here. I'll wait 30 seconds just to make sure people don't have any questions, just because this sometimes trips people up if you've never used Google Colab before.
I think the one question is if your email is not a Gmail address, you should still be able to access the Google Drive.
Yes, I think
as long as you're in a place that can access Google.
Gmail, or like it doesn't have to be explicitly Gmail, but like Google based is better. But you still be able to access all this stuff. And are there any other questions related to the drive mounting? Nope.
Not yet.
Okay, so import this OS, these system level operations here. Here you set I've set this for you. This is it points to the shared drive. It should work automatically out of the box if you click this, and then you can list all the directories inside the shared drive, and hopefully it populates. And yeah, okay, so you know that you've got this right if you see all the same folders that are in the Winter School shared drive here. Okay, great.
Just as a note, can you show them how to access the Google Drive again, the main, and how to create a copy of from your.
Sure. So you should, once you're added to the Google groups, you should be able to access this AI Winter School shared drive. So double click here, go down to the intro. For the other days, you'll go to the other folders, but today is the intro. And then you click on the IPYNB, the notebook file. You don't need to click on the dataset file. You can download it if you want. You could copy it if you want, but it's not necessary. Click on here, right click, and click make a copy. And it'll say creating copy of da 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 da. And that should be inside your own drive. So if you click on my drive, you should see it there. And the name of the file should be copy of Brown CFP, which is called da 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 da. Is that clear?
Good.
Great. Okay, back to this. So this is the path to the data inside the shared drive. So because you have read permission of the shared drive, because you're in the Google group, this should work for you. I'm logged in as a non-Brown member, so I'm doing this as a student. So if it works for me, it should also work for you. So I'm working through the Google group as well as a student. So you just set that path, and then you set this path. Because everything in Python is a string, you can just do the string concatenation here to give the full path to the data file. And then you want to set another path to your local drive. So not to the shared drive, but to your own drive here to save data. Okay. And in my local drive, I created a folder with the exact same name as the shared folder Winter School, except it just says personal to distinguish it. You don't have to do this. You can do it if you like. But set a path where you can save your work. So this will be the path inside your drive where you can save your work. And you can name this whatever you want. I recommend naming these folders within your drive the same names as the ones in the Winter School folder, just to make it easy for yourself. Again, just set this. We'll do the concatenation here, and it should list everything. Yep, module 1. That is the folder inside my drive that I created. then concatenate again, because this is the exact same name of the intro module inside the shared drive. So I'm just copying the names of the shared drive folders inside my own drive to save my work. So, okay, any questions up to here? We're just preparing the access to the data. Any questions about that? This usually trips a couple people up. It's fine if it does. Now's the time to ask questions. I'll wait 30 seconds. No?
So there was a question about whether recording of this would be available. I believe the recording of this will become available.
I think so. I think so. Yep.
But I believe it'll be on YouTube, on the Brown Physics YouTube, rather than over on the drive itself.
Yeah, right. Yeah, no, not on the drive. Not on the drive. Okay, so part 3 here, we're going to perform some data preparation. In machine learning, it's always good you should always look at your data first, right? Look at the data, what the data is, what the data structure is, look at the features, visualize your data first before you build a model and just throw the data at it. Otherwise, you're going to fail spectacularly. So we're going to use this this library you may have heard of, this framework called Pandas. It's great at handling tabular data. If you're familiar with the root, then this should be a cinch for you. So the data is in a pickle format, this PKL file format, this pickle format. So we're going to use Pandas readpickle method to read the data, and then we're going to display the data as a table. You just initiate the read of the data there. So again, I'm running this as a student. So everything I do, you should be able to do. So this full path, it links to the shared drive. And it may take a minute because the data file size is a little more than 1 gig. So hopefully this works. It was working last night. No, session crashed. No, that's not good. So what you can do in this case is you can restart. So this is actually another thing that you should learn about Google Colab. You can restart your session. And if you want to start from scratch, you can go down here and say clear all outputs. This happens if you're okay. So another thing is if you do most of your model building inside Google or Jupyter Notebook, it's good to start again if you're retraining models. Otherwise, you're effectively what's going to happen is it'll have like a kind of a memory of what you've done before, and your previous work will not get cleared, and you're going to have issues. The neural network output, the training is going to have old information in it. Session crashed without using available room. Okay, that's fine. 1 sec. So what I have done is I actually have put my my slides on the Indigo page. If there's anybody that wants to look at them, great. I did put them there. And again, my email is there. I know there are some questions that you should be able to email me about. So what I did, the first order thing to do was to go to runtime, restart the session, and then clear all the outputs. That didn't work, so I just clicked this off. I came back here, and then I reopened the notebook. Okay, and that should have worked. It should have worked because I did this last night. Right, so now I can see the data here. So I've read the pickle file, and I've displayed the data here. So you can see it doesn't. So each one of these is each one of these lists is a list of 700 samples. DS data just refers, these are just legacy names. Each one of these lists is the 700 sample pulse train. Obviously, it's not going to show you 700 samples, so it's cut it off here. On these numbers on the left, these are the event indices, the event shuffled, which you should shuffle when you train your neural network. You should shuffle the data. So if some specific types of events are clustered in one side of your data set that the neural network will see first, it's going to start to bias itself on only those types of events first. So it's good to shuffle your data before you feed it in. Again, legacy names, but this here is the delta mu. So if this is a double scatter, this is the time in nanoseconds between the two scatters of the multi-scatter event. Okay, so this is a double scatter event with a truth value 0, so it's going to be our negative class. You can see here. You might understand here that this is a single scatter event because there's no value here for the time between two scatters, and the truth label here is the positive class, the single scatter event. So we've got 200,000 events here. They should be evenly balanced, so there should be 100,000 single scatters and 100,000 multi-scatters, and we have a balanced data set. So having a balanced data set is good, generally, at least for neural networks, because you can see equal features or equal numbers of data, and hopefully this will mitigate bias. And so we can plot. I've set this up so you can plot some examples of the pulses. As I said before, it's always very good to look at the data before you do anything with it. Always look at the data before you do anything with it. Even before you do any feature engineering, pre-processing, whatever, just look at the raw data. So here you see an example of a single scatter with the truth value 1, so the positive class. And you can see it's very narrow in time here compared to the multi-scatter event, which is much wider and has the negative class. So you can see by eye the single scatter and the multi-scatter are different. So you should expect the neural network to at least pick up on obvious cases like this. But sometimes there are examples. Don't have one here, but there are examples where the multi-scatter is almost as narrow as a single scatter. So it's hard by eye to look at it, but hopefully the neural network will pick up features in the pulse that you cannot. Okay, good. So we've loaded the data, we've looked at the data, and again, this is just to get your feet wet with different things. The way that I do things here are not the only way to do it, not necessarily the best way to do it, but it gives you a mishmash of things to work, different tools to work with. So neural network libraries, libraries like Panda, NumPy, all that stuff. So this is just to give you a sampling of everything that you can use, but not in a way that you get a broad view of things. And it's not necessarily the best way, but it is a broad way. Anyway, so now we're just going to take a slice of the data for expediency. So we're going to take 50,000 events and we're going to shuffle them again. That's what this sample function does here. And we're going to get the training data, which are going to be the pulses. And so this DS data is a legacy label. And then we're going to take the targets. The target is the truth label. So 0, 1, single scatter versus multi-scatter. Collect that. And then again, we're going to turn these into an array using NumPy. Again, sometimes it's easier to work with arrays, NumPy arrays with machine learning libraries, but again, your mileage may vary depending on what you do. I just want to give you a smattering of things. So you can turn these into arrays. Just reshaping, just some pre-processing. And then we're going to, here's an important part, we're going to use scikit-learn. Scikit-learn is in the standalone AI library that has lots of very good useful functions inside of it. One of them is this train test split, which is used very, very often. What this does, it takes the data that you have here, and then it automatically splits it into a training set, so training pulses with their own labels, 0, 1, and the test set with test pulses and their own labels, and you can set the fraction that you want. So I took 20% of the total data set and set it aside as the test, i.e. the blinded set. So after we're done training, we're going to unblind the neural network on this test set and see how it does. And then we're going to create the rock curves. So we're going to create the rock curves and get the AUC from this blinded data set. And then you set a state, you set your random state here. I set it to 42 because that's the answer to the universe. And then just to make sure things look okay, sorry, I need to run. I should run scikit-learn first. And then come down here. Oops. Just print the shapes. Great. So we've got, excuse me. So we've got the number of pulses that we have with their labels, and then each pulse train is 700 samples, and we've only got one dimension here. So great. The shapes work out. You've looked at your pulses. Everything seems to be just fine now. Your data looks okay. You've got it into a state that can be read by a neural network. And so now it's time to build the model. And so this is the core of the exercise. This is the heart of the exercise. The build model function, you can call it whatever you like. I just say build model, is what creates your neural network. And your task is to select the appropriate layers and hyperparameters to build the model. So remember, hyperparameters are the things that tell you about your network structure, not the things that you train and tune, and then not the things that you learn. Those are your weights and biases. So you must select or tune the number of layers, number of hidden layers, if any. You don't have to have any technically, but won't necessarily learn anything. For the dense layers, which are the fully connected layers I showed you earlier, you have the number of hidden layers, right? Recall here, excuse me. Right, so the number of hidden layers here, right? That's something you can select or tune. The number of neurons per layer, i.e., these blue circles in the hidden layers, and the learning rate. Remember, the learning rate, which is needed to perform your gradient descent step, for your parameter optimization steps. So it's eta. So these are the three hyperparameters that you can select or tune. And then for your activation functions, you can check down here. Hopefully this still works. Oh, redirect notice. Yeah, sure. So you can look at the different activation functions that Keras offers you on its website. So you have the exponential function, ALU, SALU, JLU, which is used a lot these days. Different activation functions are here. So your job is to, and I will walk you through all of this. Your job is to tune or select these three hyperparameters, right? Look at the activation functions, check which one you want to use, and then set it on the task of performing binary classification. And then select your optimizer. Remember I said I talked about gradient descent, so your optimizers, such as stochastic gradient descent and everything else, are also listed in this link here. Redirect notice. So different optimizers here. So stochastic gradient descent, RMS drop, Atom, which I mentioned before, NATM, which I also mentioned, but a whole lot of other options. And then you also have loss functions, which you can also choose. Because we're doing binary classification, we'll use binary cross entropy. Okay, everything you need here for Keras and scikit-learn, please look at that. Finally, we won't do this, but I just want to mention, if you don't want to keep tweaking your model hyperparameters by hand, and for this exercise, if you're very ambitious, you can use two different methods called grid search CV or randomized search CV methods in scikit-learn. And this allows you to define a search space of hyperparameters for your model, and that it will go through and give you the you can set it to search the space and give you the optimal hyperparameters which are up here, and hidden neurons and learning rate. There's also something called Keras Tuner, which does essentially the same thing. But I just want to, we're not going to use those, but I just want to mention them. So what you're really doing is you're creating a function, you're tuning what the architecture looks like, the number of hidden layers, the number of neurons, and learning rate. You're choosing your optimizer, and you're going to build your model. So we use something called, we're going to build something called a sequential model here, where the layers are essentially stacked on top of each other, one over the other. There's something that you could use in Keras called the functional API. This allows you for greater flexibility. The functional API allows you to build more complex models that are not simply stacked on top of each other, but you have branches and things like that. For example, the ResNet, you'd use this to build a ResNet, but we're not doing that today. We're just using this sequential model. So this is all quite a lot. Let's go down and just be very, very concrete here. So we can define a convolutional neural network model, and it's initialized with one hidden layer, one neuron, and the activation is the radial activation function, which you can find somewhere here. The learning rate is 1 times 10 to the minus 3, which is kind of a standard choice. The rule of thumb in a lot of applications is to just kind of choose this, and then you can tune it later. And then the input shape, which is your 700 sample pulse train. So you initialize the Keras sequential model, and then you could just simply add layers on top of each other by using this add method. So I've decided I've overridden what's here, and I've now put two So technically here, okay, so the hidden layers here refer to the dense layers, so it'll iterate over this, and then the convolutional layers are on top of that. So remember, the convolutional layers have filters. You can also tune in the convolutional neural networks. You can tune the number of filters and the kernel sizes. These are other hyperparameters of the convolutional neural network. The optimizer is stochastic gradient descent, and I said before we can use binary cross entropy as a loss function to optimize. Okay. For you can either work with a CNN, or you can come down here and just use a dense neural network. The dense neural network, it just has these dense layers. Remember, the dense layer is these fully connected layers here. So you can just use these without the convolutional layers. And here you can have the number of neurons. The kernel initializer will tell you how to initialize all the parameters. There are different ways to initialize the parameters. Normal is simply one of them. We don't need to worry about that for now. Activation is the SELU activation. You can choose others, whatever you want. Be mindful of how they're defined here. ALU, exponential, JLU, whatever. But the point is, you want to tune your model hyperparameter. So how many of these dense layers do you want to add? Right? Do I want to add, let's say I uncomment this, I want to add one other dense layer. You can also tune these. Do I want 700 neurons in the first layer? Maybe I can have, I don't know, 555 in the first layer. Do I want the learning rate to be 1 times 10 to the minus 3? Maybe I think that's too low in learning rate. I can optimize learning rate here. You can change the activation of each layer, but since we're doing binary classification, do not change the activation of the output layer. This output layer is what gives you the decision. Remember I told you the sigmoid activation saturates at 0 and 1, so this is for binary classification. So you can go ahead, and what I want you to do is to choose either one of these and then monkey around with them. If you're going to do the CNN, you can add CNN layers, you can change the number of filters, you can change the kernel size, change the number of neurons. Or if you want to do the dense layer, you can basically do the same thing without the convolutional layers. Okay, so your task is to create your own model and see how you do. Okay, And what does that mean? Well, you can go down here and there are a lot of functions that are very, very useful. So once you've picked out your model, once you've decided how many layers you want, what the hyperparameters are, you can go down and have hard coded the dense layer in here, and then use this plot model function in Keras, and it'll give you um, this very nice summary table of the layers that you have inside your neural network, the output shape of each layer, and the number of parameters. So if you look down here, this is the total number of parameters, and this is the total number of trainable parameters, which means trainable parameters like weights and biases. So Keras is very nice. It gives you the summary table and how large this model is. Okay, so you can go down and you can build the model. If you want to use the CNN model, you can, but just for simplicity, I just keep it as a dense layer. And again, you can go ahead and edit this yourself, and I'll show you why in a second. Where to go? Here's the dense layer. Build the dense layer, and the Keras has another nice function where you can actually just look at how the model is constructed. So you have the input shape, and then you have the dense layers, and it gives you the output shape of each dense layer. And so this is very, very useful if you get into more advanced machine learning concepts. If you do co-design, doing FPGA stuff, and you want to put neural networks on FPGAs or ASICs, having this model graph is very, very important on how to be able to do that. So Keras is very nice. Torch does not have this natively, but there are things that work with Torch that will get you the same thing. But it's always very good to look at the data. Visuals are very, very good at machine learning. So look at the data, look at your neural network that you have here. So this is just what I have. Your mileage may vary. Whatever model you decide to build, you build that. Whatever makes you happy. Okay? So now we train the model. Now that we've defined the model, now we want to give it some data, and we want to train it. And so so there are a few things that you need to know about. So there's an optional argument in the fit function. So the fit method is what actually gets the thing going. Remember, like I said, this is kind of like this is fitting. And so when you train the model, you actually just call your model and just say model.fit. Okay. And then model is defined up here. So I call the build model function that I wrote, and I assign this the name of the model. So model.fit is what sets it on training. Inside model.fit in Keras and in other frameworks too, there is this validation split argument keyword. And what this does is it holds out a user-defined random portion of the training data at each epoch to perform a self-evaluation. So an epoch is defined one pass through the whole data. So once the network has seen the whole set of training data once, that is one epoch. So at each epoch, I say, okay, hold out 20%, and at the end of the epoch, evaluate yourself on whatever I tell you to evaluate on. Usually it's like the validation loss. So usually defaults to the validation loss. So you have, I said binary cross entropy as the loss, and then so it's gonna when I say fit, it's gonna at each epoch it's gonna take 20%. It's going to evaluate itself based on that, on the validation set. So validation set is part of the training set that it used to perform a self check, in other words, during each epoch to see how you're doing. And it's good because, well, I'll show you in a second. So this monitors the performance, and this allows you to check for overfitting after training. The other thing that I have implemented here is called callbacks. Callbacks allow you to control how the learning is performed. There are many different callbacks, and you can write your own. But two, excuse me, I have here are reduce learning rate on plateau. This is a callback that drops the learning rate whenever the model training does not find an improvement in whatever metric that you assign it. So here I've assigned it to monitor the validation loss. And after 5 epochs, after 5 full passes of the training set, I tell it to reduce the learning rate by a factor of 0.2 down to a minimum. So sometimes if the model gets stuck, can't learn, it's stuck at a local minimum, for example, or something's gone horribly wrong, you can use this callback to reduce the learning rate to try and kick itself into a better learning state. The other callback I have is called early stopping. This stops the training after a certain number of epochs, which you said, which is the patience. And this helps you reduce the chance of overfitting. A good rule of thumb is to set the patience to 10% of the total number of epochs. If you're training for 100 epochs, set the patience to 10 epochs. And again, you can use this or not, but I didn't train it for very long, so I commented this out. But this will stop the learning before the model starts to overfit, and I'll show you how to do that in a sec. And so once you've set up your validation split, you can you say how many epochs you want to train for. That's up to you. 5, do 10. You set up your callbacks, the verbosity, I'll show you what that does in a second, and then your save path. If you set the path correctly above to your local folder, it will save the trained model in this .keras file. So you can set this training. So now that you've looked at the data, you set up your all your paths, you've got the data, you've looked at the data, you've done whatever pre-processing you need to, you've built your model, and now it's time to set the model training. So remember the train test split that I have above, I'm using the training data and the training labels. So I have the model defined above, and now I'm giving it some data to look at. And so let's click go. And then so the verbosity is going to control how much information the model gives you, or how much information is spat out at you during training. So yeah, this takes quite. This shouldn't take more than a few seconds. For some reason, it's giving me nans here. But yes, to debug this as well. But so set a training. Hopefully it does something. If it doesn't, it's fine. But click this. Tell me how it goes. And then when you come here, run this cell, and it should plot plot a graph of the training history. It should plot the loss function as a function of the epochs. And it's not. For some reason, this is being very uncooperative at the moment. But you let me debug this again, and you keep going with yours, and you tell me how it's going for you. And I guess this is a good time to stop for questions as well. So are there any questions?
There's actually just one question about, in this case, this data is simulated and has labels. What would you do if you only had experimental data and it was unlabeled? Would you be looking for a classification in terms of that's more probabilistic in terms of this one is different? Would you look at something that's more like a contrast network or something?
Yeah, so there actually this is actually a very good question, because there are several things that you can do. There are unsupervised learning methods which you can implement. So unsupervised meaning you train a model without it having any labels. There are other ways if your labels are noisy or weak. There are ways under the aegis of weak supervision where you can generate labels or probabilistic labels to deal with that. So yes, you can have data that is unlabeled, or the labels are noisy and come from something not unreliable. I don't know, something like many times in astronomy, you'll get well, I won't preempt the next speaker, but labels that are noisy and don't necessarily come from the most reliable sources. There are ways to perform what's called weak supervision to deal with this issue, right? And so I hope this answers the question. The answer is yes. There are ways to do this. There are ways to deal with data that is labelless and or noisy.
Just to expand on the astronomy part, often, for example, if you're trying to classify galaxies, you're relying on humans previously tagged galaxies, and of course, if you give multiple humans, they will differ on each other, and you can use the difference between multiple humans as a relative weight to basically say how trustworthy the data is, and you'll discover that certain things are very trustworthy and certain things are not, and so the network should know not to believe all of the classification.
Is there an example on your end that you could give from your own experience, from your own?
Yeah, exactly. It was a galaxy classification issue where you trained a set of objects, but of course there isn't, the galaxies don't come with a label that says this is a spiral or this is an interacting galaxy, and so you have to rely on previous human classifications, which are not always reliable. And so there, basically what you do is you have uh, the classification be probabilistic, but have effectively some sort of weighting for the input training set. So you don't know what the truth is, but you have this is a reliable or this is not a reliable set, but you still feed everything in.
Mm-hmm. And from which observatory, for example?
This was from a dark energy camera. So this is optical images of galaxies.
Optical images of galaxies. Okay.
Just you're using the postage stamps to try to classify the postage stamped images. So these are two-dimensional data. And you're having the classifier learn from samples of images which ones are what type of galaxy.
Okay, that makes sense. While I'm debugging this, are there any questions on that? So has anybody gotten through this? Excuse me, this cell here through after the training part? Just put your answers in the chat. The point of the exercise is to spit out an AUC at the end, and you should be able to just read that off. If you are able to get that, then you should be able to just type the AUC number into the chat window, or into the not the chat window, the Q&A.
Okay, so someone posted that they weren't able to get to the subfolders in the previous task, which I suspect means that the Google Drive didn't actually make a Module 1 subfolder. So you can fix that in two ways. One is you can change the output so that it doesn't point uh, uh, at Module 1 and it can send things to my drive directly, or you can create a Module 1 folder yourself. Oh, it looks like someone made it through. And someone has a training history graph that looks empty, which suggests that the training crashed kind of the way Sean's did.
Oh, someone got the AUC. Very nice. 0.875, 0.877. Okay, very good.
And again, it's really good when you get very similar test and trains, right? Because that's a sign that you're not overfitting.
That indicates that you are not overfitting. That's correct. If other people can post that, keep posting those numbers as well. And the model architecture, if you can just post the number of hidden layers that you have and the learning rate, that would be also along with your AUC, that would be good. And I'm curious to see who can get
don't post it in the chat. Put it in the Q&A.
Yeah. Sorry, not the chat. The Q&A. The Q&A. So I'm curious to see who gets the highest and how you got the highest. And then, Jan, I don't know if people can all see each other's Q&A, but if people start putting them into the, if they can't, could you read out who's got the best so far?
I think 0.877, sorry, 0.875 test is still the best. There are a few not a numbers, which I suspect are similar to the issue that Sean has.
Yes, my apologies about this. I ran it this morning, and it's also possible that the access, it's too many cooks in the kitchen access issue.
Yeah, it seems like some people are having issues actually accessing the input data.
Is everybody able to make the plots of the pulses at least? This is the key point, and build the model and get the model graph. Can you at least get, if everybody gets to the part with the model graph, that's ideal. That is the crux of the exercise. As long as you get the model graph, everything is just hit and go, but developing the model and getting the model graph is the most important part.
Yeah, I should point out that you will have access to this. So if you can also try modifying the parameters, and after this session, try running it again.
Okay.
There's a more generic question, which is, do you ever get suspicious if you get trainings and tests that are very close to one?
Yes.
Yes.
Yes, I get highly suspicious of that, especially if so. Okay, this is actually an excellent question because it gets to something that I didn't go over here, and that is leakage. So data leakage is a phenomenon where your model is learning on a feature that you didn't give it. So for example, if it is in the context of this exercise, the pulse classification, we're giving it features of the pulse, like the pulse height and the noise or something like that. If, and you should go home and take a look at this yourself, if you integrate the pulses and get the pulse area and perform a histogram, create a histogram of all the pulses, um, of all the pulse areas, you will see that the areas for the multi-scatters are much larger than the areas for the single scatters. So if the neural network starts learning about that, and you didn't give it, then that is a form of leakage. There's also there are different sort of types of leakage, like labels or split leakage that comes between the test and train splits. So if you get a suspiciously high AUC, then yes, you should be very, very suspicious. And then you should look for that. Look for leakage. Check your data pre-processing. Check the features, et cetera, et cetera. Okay, I have somehow been able to do this. I don't know exactly what I debugged, but I did debug it. Okay, so hopefully everybody at least got here. And then so I'm actually just running inside the drive itself. So I was able to train, and so I was able to train for 3 epochs. And then after 3 epochs, you can watch the loss gradually reduce. And you can monitor the validation loss to see if it reduces similarly. So the loss is the binary cross entropy, as we had above. Because it's a binary classification task. And so you can watch the train. You can set this to a higher number of epochs if you like. But the point is the verbosity will tell you, set the verbosity, and it will tell you all of this information. So if you're getting something much higher than the 15 seconds or 16 seconds per epoch, check, I'm not sure, check the amount of data you're using. Maybe you're using more than the data that, because I sliced it to like 50,000 or something above, check that that's correct. Check the model, your model may have gotten too big, but
Yeah,
for
some
the,
of it also has to do with the complexity of the model. You can build a model
exactly,
that trains very, very slowly.
exactly. But the point is, if you set the verbosity, you can see the loss decrease. And if you plot the loss history, and there are only 3 points here, you can look at at the loss.
Oh,
So the
you're currently not sharing.
I am not. I'm sorry. I forgot to click share. I'm so sorry. So if you plot, if you can look at the loss here, you can see the loss decrease, and the validation loss is the one that you want to be watching because it looks at this held out split here. Check the validation loss. And then you come down here, and I've set this up so that you can plot the loss as a function of epoch. So the blue curve is the loss, and the orange curve is the validation loss. So if you look, the x-axis is the epoch, and so there's only 3 epochs. I said you could set it to more, so you can have a better curve, but you can watch the loss gradually decrease. So the orange curve is the validation loss. If you find that the orange curve starts to tick upward, but the blue curve, the loss, if the validation, i.e. the the orange curve here, starts to tick upward while the blue curve kind of remains stable, that's telling you you've got overfitting. And you want to avoid that by using what the callback such as early stopping. Early stopping will stop the training before the validation loss starts to tick up again. So ticking up just means that the the loss starts to tick up. That means you're starting to overfit, and that's why the callbacks are important. It's one of the ways to mitigate overfitting. So I've got the callbacks early stopping here. I don't have 5 epochs, so the early stopping condition is not going to be met. But if I did change it to 5 or more, like 20, 30, 50 epochs, then this validation will be this callback will be initiated. And so you get that. And then you come here, and then you take the train model, and then you use the predict method on the test set. So remember, the test set is the blinded data set that we split earlier off the main data set. And then you can run the predict. I've set this up for you to plot the rock curve. Don't need to mess with that. Although this is the function you should be know the rock from sklearn, the rock curve, and the rock AUC score. These are all methods from scikit-learn that I've implemented for you. And you should be able to come down, and you should see a curve like this. So I get from the default model that I had developed above, I get this rock curve about the same as other people had gotten, 0.87, 0.74. And the curves are close together, indicating no overfitting, but they're above the 45-degree line, which means that the model did actually learn the difference between single and multi-scatter pulses. So it can actually tell the difference between signal and background in this case. And that's all based on this simple model here. I use the dense model here, so not the convolutional one. But it's still, this simple model still performs very well on the simulated pulse data. So I'm curious to see what other people got. That's essentially the hands-on to get your feet wet. 0.871. Yeah, so people are asking where can we post? Just post in the Q&A. I will be able to see it. So 875, 871, 872 for the train, 874. Yep. Yeah, so the error, yeah, so the full path, you have to, so the way to deal with the full path issue is to write the full local path is the path in your own shared drive. So you can create the folders that I have set in the that I have labeled in that I have set inside the notebook, or you can change it to just the top working directory. So like just change it to // or something like that. Values of NaN, I think this is like just an access thing, because I was able to do it from the main drive that I have access to. So I think this is just too many people trying to access at once. But people are just give it a few minutes and restart the notebook and rerun it, and you should be able to get it. Let's see, 8740, 7.3. Yep. Good. People are actually starting to get things. Very nice. Okay, fantastic. This gets to the end of the hands-on. Sorry about the hiccups that we had here, but hopefully people have figured it out or are figuring it out. If not, there you can please feel free to email me at any time. My email's in the slides. What are there any final questions that people have about the hands-on, about the basics here?
So there was one question about if the validation loss goes above the test loss and then starts going down, is that an issue? There is a certain amount of randomness, so I would imagine
it's not always just smooth down. There is some randomness depending on how noisy your data is and how you initialize the model. So you can see like this. It'll spike up, it'll go down. It won't always be smooth. It depends on the data. It depends how you initialize the weights and biases and all that. So you don't expect it to always just be a perfectly smooth, monotonically decreasing curve.
There was a question about the video of these sessions. They're going to be uploaded to the Brown University Department of Physics YouTube channel. My understanding is that they're uploaded relatively quickly. I cannot promise that they'll be uploaded tonight, but it's not a question of weeks.
So any other questions? I'm happy to answer. There are other sessions tomorrow. So physics informed neural networks. The presenter knows a lot more than I do. If you're interested in that, go there. There are other interesting, diverse topics as well.
Yeah, we've tried to keep a variety of topics, so you'll see different implementations. So I think at this point, I would move that we close this session. We'll meet again at 10 o'clock tomorrow for Brian Ostadek from Microsoft Labs, who will be presenting on physics-informed networks. So there'll be a session tomorrow at 10 and another one at 2, sorry, using the same Zoom channel and using the same Google Drive, but obviously in different modules. So hopefully so thank you, Sean, and hopefully you had a good introduction both to the ideas of machine learning, but also to the way the winter school formatting will work. Thank you all.
Yep. Thank you all. Thanks for coming. Please attend the other lectures. They are very good. All the lectures are very good, and I'm sure you will enjoy them and get a lot out of them. So thank you again.